Hello everybody and welcome to this last lecture on functions and graphs. We're going to be looking at related graphs. So a lot of what this is it's going to be zoning in on something we've already talked about when we were going through sketching graphs of functions, and that is graphs that maybe have the same roots but are not the same, or they might have very similar characteristics, however are not, let's say, congruent or exactly identical. So we'll just get going straight away. Okay, so the first thing we're going to look at is we're going to look at any function f of x where we add a constant or else take away. So we're going to say add or take away a constant. So what we can see from the graph is that we have three different functions. So we have start off with f of x, which is x squared. Then we have g of x, which is x squared plus 2. And then we have h of x, which is x squared minus 2. So what we can see about g of x is it's actually, so it's x squared plus 2, is that it actually is f of x plus 2. So it's just the original. So I just named f of x the original with a positive constant. And then we see for h of x, it's f of x with a negative constant. And what we see is that, so g of x is a translation of f of x vertically upwards, and then h of x is a translation of f of x vertically downwards. So one of the key things to notice is that when we have the equation of a line, y equals mx plus c, I've always said that c is where our graph intersects the y-axis. So whatever, or whenever x is equal to 0, the y is going to be your constant. So we see that here. So we see that the red graph cuts it at 2. We see that the h, or the green graph, cuts it at minus 2 on the y-axis. So that's exactly what we're doing. So if you see there, a positive constant moves the graph positively upwards on the x-axis, and a negative constant moves the graph negatively downwards on the y-axis. So think of it like this. Let's say you are running a business and you have a function that, let's say, y is profit and x is the number of units sold. So let's say x squared plus 3x, let's say minus 5. So what we need to know is if we don't sell any goods at all, we get y equals 0 squared plus 3 by 0 minus 5. So if we sell no goods, we end up getting a profit of minus 5, which makes sense because obviously there's some inputs like buying raw materials or whatever. So if you sell no goods, well then you're more than likely going to make a loss. You probably won't get 0. So that's exactly the way to look at it. That if you sell nothing or nothing happens, or basically x is equal to 0, is that generally we won't have our y equal to 0. So generally there is some kind of constant. So when we look at the graph y, which is fx plus or negative a, so what we see is that, so we have the three graphs. So I kind of did something similar where the original was our y equals x squared, and what I've done is I've used the same rule, so a certain number squared. So when we add 2 inside the, so everywhere x is, what we see is that it moves the graph to the left by 2 units. So you can see it's, as opposed to x squared, it's x plus 2 squared. And we see the same when we do minus 2, that it goes from being here and it moves 2 units to the right. So what we can kind of come to the conclusion is that when we have a function, so y equals f of x, so let's say is the original, then what we get is that if we put an additional number where x is, so let's say x plus a, then it results in a translation parallel to the x-axis of a negative of that amount. So we see to the left, and then if we do y equals fx minus a, it results in a translation parallel to the x-axis of a positive a, so it moves to the right. So that's just something to bear in mind. A negative will make it a plus. Now that might be difficult to see in something as kind of easier. It's kind of a once off of an x squared, but if I just show you this graph here, you see the same thing. So you see that we have a function, let's say f of x equals x cubed minus 3x plus 4. So all that g of x is its f of x plus 2. So everywhere we see x, we put in x plus 2. So this goes here and here. And then h of x is the same thing, except it's f of x minus 2. So it's the same thing again. And what we see is they're the exact same, or they follow the exact same path, except each of them is, so if we just take this point, for example, the h of x, which is x minus 2, will move it to the right, okay, minus 2. And if you see the g of x, it will push it, so even though we're adding 2 inside the function, it's going to push it to here, to the left. So that's just something to bear in mind. So sometimes it's a bit tricky to see when you just use the x squared, but when you actually have a longer function, you're going to have to put the x minus 2 into 2 places, or wherever the x is, you're substituting in x plus 2. So that should give you kind of a slightly better understanding than just the x squared. Okay, so for our next one, what we're looking at is some function y, or some output y is equal to minus of a function f of x. So what we see is, let's say our original is f of x, which is x squared, and our kind of altered is the minus x squared. So what we see is they're very similar, except one is a reflection of the other through the x-axis. So you can see that they are basically mirror images of each other. So mirror images. So we can say g of x is a reflection in the x-axis of f of x, or in a more standard, the graph of y equals minus f of x is a reflection in the x-axis of the graph of y equals f of x. So moving on, now we're looking at the graph of y equals minus f of x. So we said f of x is x squared, so we're sticking to that. But in this case, what we're doing is we have a g of x which is equal to a negative of the graph, or negative of the function. So what that does is it causes a mirror image, okay, so it causes a reflection in the x-axis. So g of x is a reflection in the x-axis of f of x, or a more standardized way of saying it is that the graph of minus f of x is a reflection in the x-axis of the graph of y equals f of x. And then, so another thing we have, so they're similar, is this. So if we have g of x equals f of minus x, okay, so it's very similar to, let's say, this one here. So here we were adding a number to, or like when we substitute in for x, we're substituting in for x plus a number or negative a number. But in this case, what we're doing is, instead of having x plus a, we're just doing negative x this time. So when we do that, as opposed to a reflection in the x-axis, we see a reflection in the y-axis. And that's shown by the yellow line going down here. So we can see that g of x is just f of x with a negative in front. And it results in a reflection to the y-axis. Again, we have another mirror image, and we see the graph of the y equals f of minus x is a reflection in the y-axis of the graph of y equals f of x. So very similar to this, except we have a negative outside the function, whereas in here the negative is actually part of what we input. So that's a key difference. So we'll just move on to the very last one. So the very last thing we're going to look at is what happens when we have a f of x. So let's say we're multiplying the function by a constant or a certain number. Well, what we see is that the roots of each function are still the same. So we can see that, so we have f of x, g of x, and h of x. So we just have the original function, and then we have the function multiplied by 2 and the function halved. And they all have the same roots here and here. So they have two real roots, but this one here looks like it's being shared at the 0 point. So right here. So it looks like we have, they each have roots of x plus 1, or sorry, well, x equals minus 1, so x plus 1, and a factor of just x squared. So that looks like the function we have. However, what we see is that the minimum or the maximum points are all different. So we have a maximum point here, here, and here. So if you actually got up your calculator or measured this, you'd see that the elevation is twice as big here. So let's say we can see that it's similar to, let's say, 1.5, and then this max is exactly 3. And then what we can see from here to here is it's actually a half, or divided by 2 down here. So it's about 0.75. So we can see that the roots are the exact same, or it doesn't change where it cuts the x-axis. However, the points are amplified or condensed depending on the number we multiply it by. So if it's a smaller number, if it's a number between 0 and 1, it's going to be condensed, and if it's a number greater than 1, it's going to be amplified. And that's going to be important when we look at sine, cos, and tan graphs, and more kind of graphs in paper 2. So that's all for this lecture. It was kind of long, but it's important to know, and not only would it help you with this topic, but it will actually help you kind of understand when you're working with, as I said, paper 2. It will help when you're looking at even kind of calculus and things like that. You'll kind of notice that you'll start looking at things saying, oh, I know why that's the case. So that's kind of why I left this lecture till the end, is that you can kind of now start to see as you go over some of the questions, like, oh yeah, even though I didn't really know that when I was looking at the other topics, now I can understand why this is the case, or why one graph looks as it does. So thanks everyone for watching. This is the last lecture if you followed the course from the beginning to the end. So I thank you for watching, and please check out the questions at the end of the course. So it has some exam paper questions for each topic up. So please have a look at that, and hopefully you find that helpful. So thanks everyone for watching, and I'll see you soon.